I was just having a look before with Josh, but it's now up to 1.4 million views on YouTube, which just shows, there is actually quite a lot of interest in computer science beyond what sometimes it feels like. Yeah, and so what happened was, initially we were going to start producing the Raspberry Pis ourselves, and obviously when we got 100,000 pre-orders, the amount of capital we need to do that was a lot more than we had. We were bootstrapped. There's no VC money. There was kind of no. It was all our own financing, and so we partnered up with RS and Farnell and work on a licensing model where we license the design to them and they manufacture it and distribute. Initially, some of the manufacturing, initially all the manufacturing was done in China. Now all of the manufacturing, certainly of boards which are being sold outside China, is done in Wales, in the UK. Which is very cool. It's cool that the cheapest computer you can buy is manufactured in Britain. You wouldn't really think about that. And we've moved that manufacturing from China to the UK. It's a pretty cool thing. And yeah, we sold about 1.5 million units of these now, all around the world. And that's a great thing. And as I say, it was designed with this aim of promoting computer science. We're very passionate about trying to get everyone to realise that programming, a bit of programming knowledge is valuable for just about any career these days. And equally, we wanted to make sure that students, like there are many here, could afford to build those robots they always wanted to and still have enough money left over for beer. That was kind of our noble quest, right? And and I think we've come a long way to achieving that. So I would ordinarily at this point go through a lot of the technical specs, but I have a feeling most of the people in this audience will probably already know them. So what I think we'll do is I'll let Josh talk about his project, and we will cover some of the technical aspects as well, and then hopefully have lots of time for a Q&A afterwards. Great, so Josh.
Well, I'll try to keep it short so we have lots of time for questions. I actually have a huge presentation here that but I'll just skip through a lot of this stuff just for the sake of time. So I'm a PhD candidate here at Boise State University, and I'm working in wireless sensor systems. And so I normally wouldn't have a whole lot of reason to use a Raspberry Pi because we're always designing, at the with microcontrollers in very small embedded systems. But when I started looking into developing some new communications protocols for wireless sensor networks, I came up with this idea that, well, it'd probably be easiest to test a lot of these ideas if I could just create a simulation that would allow me to do that, test all these ideas. And I thought, well, what's the best way I could do a simulation that would best emulate the wireless sensor nodes that I was working with. And I thought, well, what if you have a application running on each node in a cluster, and all of those communicate over Ethernet, but the scope of their communication is limited in the simulator to emulate that of a wireless sensor network. And so that's kind of how I got started in working in a cluster environment, but still on protocols for use in wireless sensor networks. And so on campus here we have a big Beowulf cluster that has 32 nodes. Many of you guys, if you've taken any computer science classes, you've probably been in the Onyx lab. How many people have actually been in the Onyx lab? So most of you people over here. So it's just regular desktop computers. They're all hooked up on the same network, and you can actually issue parallel jobs against those computers. They'll all work on the same problem and return the results. That's basically what's going on. Go back through here. So for anyone unfamiliar with what a Beowulf cluster is, really it's just a bunch of regular computers that are connected together through a common network. And they have some bits of software on there that allow them all to communicate with each other and share data and share processing. Virtually all of them use some kind of Linux-based operating system. When you want to write programs that capitalize on all these processors, you need some way of doing that, and that's what this MPI language is. It's basically just a set of tools to write programs that allow you to do parallel computing. And so as an example, like I said, Onyx Lab has 32 nodes. They're all quad-core Intel processors, a whole bunch of RAM, and they're all running Fedora, which is a Linux distribution. And I kind of covered this. So the question is, so why would I want to, if I have Onyx cluster, why would I want to build my own cluster? And really this came down to, so 1 week during spring break this spring, Onyx was unavailable for me to use because they were doing some renovations in that room. So I got thinking, so I have this long-term project that I'm working on that requires a cluster. How can I ensure I always have a cluster available to me and one that I can customize in any way I want? And so as soon as I got thinking along those lines, I was like, well, what kind of hardware could I build a cluster of my own? How cheap could I do it? And we had recently been playing with Raspberry Pis a little bit in some of the work that we do in our lab as basically servers. So we'll connect our wireless sensor nodes to Raspberry Pis that upload data to central servers. So we had some lying around, and I go, well, let's see what we can do with that. So that's how this whole thing got started, was building a little cluster that could run my simulation and do so for as little cost as possible. And then there's a couple other things that you get with the Raspberry Pi that you wouldn't get in a normal desktop computer. And one is, you'll notice up here these LEDs that are blinking on the side. Well, that's actually coming from a PCB, custom printed circuit board on there that we put our own LED on there. And its primary purpose is actually to allow the whole thing to be powered by regular computer power supplies. Normally a Raspberry Pi is powered by the little USB connector that's on the front. So all these are actually powered through that little board. And so aside from being able to toggle LEDs on and off, there's also these other hardware interfaces, the I2C and SPI. These are all common communications protocols used in embedded systems to talk to other kinds of chips. And that's useful for what we're trying to do. So the kind of idea of what was involved in creating this, basically you need 33 of a lot of parts. So we got 33 Raspberry Pis, and similarly, we got a whole bunch of SD cards, one for each board. Lots of Ethernet cables. This box on the bottom here is a big switch. So all those Ethernet cables run into that common switch. And again, we had to design that PCB that provides a way to distribute power to all the nodes that are there. So in terms of software on here, I'm running Arch Linux, which is a very lightweight version of Linux. It's kind of the bare bones distribution. So when you first install it on your computer or on your Raspberry Pi, you can connect to the internet and you have a basic command line interface, and that's it. There's no desktop environment or anything pre-installed. It supports all the other features that you can get in Raspbian, which is the most common Debian-based Linux. But the nice thing is that you're starting kind of on a clean slate. You just add only the things that you want. And the benefit of that is it only takes about 10 seconds. 10 seconds for one of these to boot up from a cold boot, so very quick. And how many of you guys know that you can overclock the Raspberry Pi to run at higher speeds? A few people, yeah. So all these are overclocked to run at 1 gigahertz rather than their normal 700 megahertz. And this is something that is supported by the Raspberry Pi organization. They're rated to do it, but they don't ship them that way. So, and as far as software required, I basically just I wanted to be able to do parallel programming. I wanted to be able to have a shared file system with all of them, run Java, Python, and Perl. So this node up here is providing a network file system for all of the other ones. So the other ones, anytime the master writes something to its file system, the others can see what's there. And so these are just some of the packages that I installed on there to achieve the only things that are necessary to install to get a working cluster. And this kind of gives a graphical idea of how it's connected. So you have that switch, which all of those pies are connected to. And then the master node, which is that one on the very top there, is providing the network file system for the rest. So pretty straightforward. And I'll skip over some of this stuff. So I talked about that little PCB board that's on the top there. And that's the circuit that there's. The center block there, that's just the header that has a bunch of pins on there. All I'm really doing is providing a way to get power into the board and drive a tricolor LED that's on the other side of it. So that's the Eagle CAD picture of it, and that's a very blurry picture of PCB up close. And then, so in the process of this, I was trying to figure out, well, how can you put all of these, you got 33 of these things, how are you going to stack them in some orderly fashion? And so I came up with the idea of using PCB standoffs. So these are the type of things that normally would mount like the motherboard of your computer inside the case and hold it. That's what these basically are, just extra long versions. And so they're just threaded all together to build these stacks of 8. And then in order to keep all those stacks together, we decided to cut some plexiglass. So this is plexiglass on top here. Designed a little footprint in Eagle to lay out where they would be and drill the holes where they need to be. And so with that, I was going to show a couple little demos. The first one, this key link one here, that one's already running right now, so you can kind of see what it is too. And effectively, so it's one program is written, which is started on this master node up here. And basically what happens is when you start the program here, the application gets spawned to all the nodes that are below it. And once they're all up and running, they can all share data and process them together. And all that's going on here is this node is sending commands to each of the ones below that are slaves to it to tell them when to turn their LED on and how long and what color they should do. And so anytime you see cases where multiple LEDs are turning on at the same time, the reason they can do that, since each of these are independent processors, right, but they're able to turn on at exactly the same time, that's because it's able to send a broadcast message over the Ethernet to tell it when to turn on. So that's the basic idea. So, so the last thing I'll just show, just to give you a little idea of how easy it is to do GPIO type thing. So turn on an LED, I'll terminate that. Alright, so this is going to be fun because I didn't clear my monitor. Okay, so if I want to say turn on the LED on this board right here, I can do that with actually just some basic commands. So you can. So first off, I wrote a program. That do this. That just does one